Um,
Who needed it?
yeah, it's all garbage anyways. All right, so here's one for you guys. Let's imagine I have, um, let's say we have a hollow cylinder, and let's say there's current going down this one, and we're going to make it coax. So this is empty though, empty in the interior. Okay, but there's current running around the outer edge, and then we're going to wrap this with another cylinder. We're going to have a gap that's empty, like that. And we're going to take this to be very long. So this is a very long coax axial cable. I want you to tell me what is the magnetic field everywhere.
Hey Sean, is this
Yes.
similar to like the two solenoid question on sapling?
Uh, no, no, that one's pretty easy because inside a solenoid, the magnetic field is just constant. And so if you're in the middle of both of them, you just add the overall magnetic field of both of them to get the final answer. And if you're in the gap between them, you just get um, the outermost one.
The outer one?
Yeah,
Okay.
but it's that's a really easy one. All right, so this one is how do you find you're going to use Ampere's law. So and I should say this, I have current flowing up the outer wall. So I have current going down the inner one and up the outer one. So first thing is, which way do the magnetic field lines flow or orient themselves? So how do you figure that
Um,
out?
you go with your right hand.
Yeah, and how do
So
you?
you just grab it and point your
Yeah,
thumb in the direction of the current.
and if we want the magnetic field, well, first off, what's the magnetic field inside this cylinder in the middle? Well, to figure that out, um, to figure that out, sorry, um, the so I would draw a little like in the interior. I draw a little Amperian loop. What color to choose? I'll choose blue. Right. So draw a little Amperian loop in here. How much current goes through that loop? Well, it'd be zero because all the current flows on the outer walls of the cylinder. It is empty in the middle. So then that
Hey
means,
Sean,
yes.
it sounds like you're talking like miles away from your computer right now.
I'm like
Oh, there we go.
I'm like
Wait, there we go. It's better now.
yeah.
You sounded just really far away, like you didn't want to be here or something.
Thomas, did you say something? I can't hear. All right. So if there's no current in the center of the wire, that means that the magnetic field will be zero in the center. So now what about the gap? You'd want to draw an Amperian loop in the gap, like that. And now how much current passes through? So first off, you want to grab the wire or the current that flows through. So you want to grab it with your thumb going down. And we see that the magnetic field lines are going to go this way, right? Because if I grab that central line of current, my fingers curl around it with that orientation. Raise your hand if that's clear. Otherwise, I need to explain that better. Okay, most everyone. All right. So now, if we're taking this to be a very long cable, bordering on infinite, then the magnetic field line can't differ as you go up and down. You could draw this loop anywhere in around the or anywhere in the coax cable. You should get the same answer. And it can't depend upon, by symmetry, it can't depend upon what angle you are around the wire. So that means that the magnetic field is constant as you go around this wire. So that means if I do work out the integral of B dot ds around this loop, that should equal mu naught times I enclosed. But this loop wraps around all of the current I, so this is just going to be B times 2 pi R equals mu naught I, or B equals mu naught I over 2 pi R. Same answer we had for just a wire, even though now this is, so this is not quite a wire. I mean, it's got some thickness. And so this is going to be the formula for the magnetic field in the gap. And then on the outside, I do the same exact thing. But when I do that, if I draw the Amperian loop on the outside, the current enclosed is 0. So the magnetic field is 0. Okay. So that's kind of how you use Ampere's law to do these things. And using Ampere's law is a lot easier than it is to use Biot-Savart, if you can. All right, I want to go through the Helmholtz question here. Switch over to sapling here in a second. So I want to do currents, Helmholtz. Okay, so let's see here. So the Helmholtz question, the Helmholtz question, so they give you two Helmholtz coils, and the current goes that way. So the total current here is like N times I, and it's the same over here. And they want you to find a formula for the magnetic field right in the middle. And in their example, R, so in their example, they choose, I've not drawn it to scale, they choose, so this is a distance R, and they actually choose the separation to also equal R. So in my example, I worked it out with R and L, but they choose them to be the same numbers. So I worked out a similar, okay, and then in the picture, they want you to say that this is X equals 0, and this is X equals R. I did a similar kind of problem where I put X equals 0 in the middle, and I put this one at X equals minus L over 2, and this one at X equals plus L over 2. So, Brian, I think what I would say is if you take my formula, replace L with R, and then also take my value of x and replace it with x, let's see here. What I call 0 is going to be r over 0. Hold on a second. It's going to be r over 2. Yeah, so replace x with minus r over 2, I think. Hold on. Yeah. So I think, Brian, if you take my formula, replace L with R, and then everywhere I have X, replace it with X minus R over 2, that just shifts my configuration to align with their configuration. Is that, I don't know, is that what you were asking, or was it something else? Let's see. Okay. Otherwise, the rest of the problem is just you use the formula for a loop, for a loop. Oh, and you know what? In my problem, I use Z, not X, but that's just cosmetic. So you use the formula for, if I have a loop of radius R, and you want the magnetic field right in the middle at some height Z, then the formula for the magnetic field, that's the one I used on the first example I was trying to show. That's going to be mu naught times mu over 2 pi times 1 over, and it's going to be R squared plus Z squared to the 3 halves. And they don't use, that's what I did in the video. They don't use Z, they use X. So you just replace X with Z with X. And then the other thing is, for a Helmholtz coil, you've got 2 of them next to each other. And the reason you do that is because it produces a very uniform magnetic field. So this gets used in a lot of experiments. If you want a constant magnetic field, you do this with the currents going the same way. And then there are other experiments where you want a linearly increasing magnetic field for various reasons. And when you have that, you would just reverse one of the currents. So this configuration gets used a lot in experiments. Um, so, so anyways, the way you get the formula for that. So you add the two. Oh yeah, that's right. So it's magnetic fields behave kind of like electric fields. So if you have a complicated configuration, you find the 2 separate magnetic fields and then just add them. Yeah. Yep. Same idea. The hard thing about this one is that you have to kind of add them, but they're not centered at the same place. So you have to kind of offset where you center the rings. Yep. Okay. Are there other questions on the sapling?
Oh, Sean, can you go back one slide when you were to that other one you had?
This one? Oh, sorry. Which one? This one?
Yeah, that one.
Yeah. So first you need to replace Z goes to X, and then X goes to X minus R. And all that's doing is, they want you to put the 2 rings at X equals 0 and R, but the formula I worked out was for centering them at like R over 2, minus R over 2 and R over 2. So you just have to shift it by a half of a radius to get my formula into their formula.
Okay.
All right. Um, is there any other questions on tonight's, or yeah, for the next sapling? Okay. If there aren't any questions, I want to kind of set the stage for what's coming next. And I'll post videos on induction this weekend, but I want to kind of set that stage. So what we've been talking about with Biot-Savart and Ampere's law tell you how to find the magnetic field for a current, but all of the currents we've been talking about are steady. And that's called magnetostatics, because it produces constant magnetic fields. It turns out that there is an interesting effect where if, let's say you take a magnet, okay, so it has magnetic field lines like that. And if you were to put it in, like have a wire right here, and if you were to move the magnet towards the wire, can't spell, what actually happens is that a current will start to flow around the wire. So as you move the magnetic field towards the wire, current starts to flow around the wire. This is what you use in a generator, right? In a generator, what you spin a magnet, but you move a magnet and then it causes electricity to flow. So this is encapsulated in something called Faraday's Law. And the statement is the following. So I'll explain here in a minute. So I'll write the formula and explain it. But when this current flows, there has to be an EMF around the loop. Hopefully I got that right. I may have to have it backwards. So the statement is the following. The EMF around a loop equals minus the time derivative on the magnetic flux through the loop. So this is explicitly a time-dependent thing. If the magnetic field is constant, if everything's constant, this is just zero, and this is not something you would ever see. You have to have things in motion. You have to have some sort of time dependence. That's really what you need.
Hey,
So
Sean, I know you might have said this before, but is for magnets, is it always the magnetic field lines point from north to south?
yes, they come out of the north and go into the south.
Okay, thank you.
Now think about that, just on an aside. If you have a compass, the north end, there's a little magnet in the compass. The north end of that compass points towards the Earth's North Pole, which means that magnetically, at the North Pole of the Earth must actually be the South Pole of the Earth's magnetic field.
Then why didn't they just name them the other way? Just because we've always known north is up?
Well, I mean, I don't think, because they didn't know the underlying cause, right? This was discovered by
makes
looking
sense.
at lodestone and stuff. And
So
so,
I didn't even know that. So you're saying that the south pole is the north part of the magnetic field?
yes, the
Okay.
South Pole is actually where the Earth's is the north of the Earth's magnetic field. That's right.
Why is that? Oh, is that just fact?
Well, think about it. If you the north end of the whatever direction the north end of your compass needle goes has to be the south of that object's magnetic field because they're attracted north to south. So, yeah, it's just how it is. Okay, so this is kind of a weird thing, and here's a way to think of it. A better way to so what I tried to describe, this is physically what you would do. What's actually happening is the following. Imagine you had a loop, a wire, okay, and imagine that there are magnetic field lines kind of going through it. Okay, and then okay, so that's fine, and it could just, that if that's all, if it was just stationary, there's no time dependence, then there nothing else would happen. But if you try to add an extra magnetic field line through the loop, if I try to do this, if I try to add more lines, what actually happens is that there will be an EMF, which around this loop of wire, the EMF will point as if it's trying to prevent you from adding the line. So it's going to produce, in fact, if this was a physical wire, the EMF would give rise to an actual current flow. So you would get a current going around like that, because so I'm adding this. Let me make it really clear which one I add. Let's say I added one more line going up, and I'm going to make that one kind of bolded, thicker, right? So I added one extra line. The Faraday's law says that the EMF will be generated so that, if you were to put a wire there, hypothetically, that EMF or that potential would cause the charges to move. And the way I always think of it is the magnetic field that is induced in the second loop, the one that started to flow, tries to counter the original primary one. So it would create a magnetic field line which would go around and then down on the inside, and it would go around and down on the inside. So the idea is if you try to add more lines, the current flows in a way that generates kind of a canceling magnetic field of its own. I'm not saying this very clearly. I apologize. Raise your hand if you're totally confused.
I mean, I think I know what you're saying. So,
So
like, if we put our right hand on that, the magnetic field lines that wire is producing
yes,
is going against the magnetic field that you're pushing through.
yeah, the added one. That's right.
So, how much of an effect does that have on it?
How much does it have? Well, the strength of it depends upon the resistance in the wire and things. It depends on how much current you actually get. So the statement. So I said it. I remember I kept saying as if, or if there's a wire, what would happen? I do that so that I can remember which way things point. But the actual law doesn't require there to be a wire there. Okay, nothing in here says there's a wire. When I said loop, that could be just a geometric circle or something. So you don't need a wire, but if there is a wire, it does what I said, and that
So,
helps.
what's the? Oh, sorry.
And that helps me kind of get the orientation of things going. Okay,
So for Faraday's law, that's epsilon. That's what does that epsilon stand for?
this is EMF.
Oh, the EMF.
That's like a voltage. Yeah.
Okay, and that equals the rate of change of the flux.
With a minus sign. The minus sign is that oppositional character. The minus sign is called Lenz's law because it was discovered first. That's why. So the fancier way to say this thing is to think about why would the current flow at all? And the statement is this: when you add extra magnetic field lines, What's actually happening is you're getting electric field lines which wrap around them. That's the better way to describe it. So the better description is that when you have magnetic field lines, and if you try to add more, if you try to add one more, then you actually generate an electric field line which wraps it around it. And then if you put a wire there, that electric field causes a current. But the real effect doesn't really have anything to do, well, it's not really an effect of currents and of currents, it's really an effect of electric fields. So when you add electric field lines, when you add magnetic field lines, then you generate electric field lines which wrap around it. And these are new types of electric fields. First of all, they're new because they're time dependent, but also what's different about this kind of electric field versus anything we've seen so far?
It's green.
No. It's a loop. So it's not caused by a charge. Forms a loop. This kind of electric field is very analogous to these loops of magnetic field lines we've been talking about. And so what we're seeing is that time-dependent magnetic fields create electric fields. Charges create electric fields, but so do time-dependent magnetic fields. That's called induction, the creation of one effect from another. You basically, by having time-dependent magnetic fields, we have induced the presence of an electric field. And so it's kind of, yeah, it's tricky to wrap your mind around. What's going to happen is, so time-dependent magnetic fields will create electric fields. It turns out that time-dependent electric fields create magnetic fields, and then you can set up oscillations back and forth. You can have time-dependent magnetic fields creating electric fields, which create magnetic fields, which create electric fields, back and forth, back and forth, back and forth. That's called light. And that's what we see with our eyes. So that's kind of where this is headed shortly. All right, so I'm going to post videos on that. Hopefully I'll do a better job explaining it in the videos. I think I kind of botched it here today. Read up, I would say read up in OpenStax. I think they have some good images and figures to look at, kind of help you get oriented on things. The hardest part about this stuff is orienting things in 3D, because you have loops, right? We have, like in this example, we have magnetic field lines and we have loops around it, and then we have loops on loops. So it gets really tricky to picture things. And so really work on that. All right. I think I'll leave you guys there. Okay. So I will post the videos, and hopefully that will help clarify things for induction. All right.
See you, Sean.
See ya.